All right, let's talk about coroutine implementation in MLIR. I've split it into 3 parts. So first, want to define the problem and give a little background on asynchronous programming. Then we'll explore LLVM's solution to coroutine and why it didn't work for us. And finally, we'll look at what we had to do to design coroutine lowering in MLIR. Okay, so first part, I'm gonna start with a really familiar problem of trying to do some compute and ask for user input. So given some user input, we're gonna kick off some kernels and wait for them to be done, and then we're gonna do some other work, which is simulated with just printing to the terminal here. This first stab is synchronous, so the first task, gather user input, then we're gonna kick off some kernel computation by writing the command buffers, and then we're gonna spend a bunch of cycles just checking status registers. And finally, they'll be done, so then we're gonna write some more commands, and then we're gonna spend some more cycles just checking the status registers, and then finally, it'll be done, and we'll simulate some other work. But this is obviously really bad because we just spend a lot of time spinning, and we'd like to not block the main application. We'd like to interleave the task something more like this. So this is, we'll check the status. It's not done. We'll do some other work. We'll go back and check it. We'll do some other work. So what do we have to do to accomplish this? Well, I had to introduce some states. I had to turn my function into a state machine. And then I had to write a struct to store all the intermediate state. So there's a lot of work to transform this into something that's interleavable. And it's too much boilerplate, it's tedious to maintain. But luckily, compilers are really good at tasks like this. And in 2012, C# popularized the async await pattern. And it's since become the industry standard. So a lot of languages, including Python, Kotlin, Rust, C++, Swift, and now Mojo have adopted the pattern as well. And as you can see from the labeling, a lot of these languages use LLVM as their backend for coroutine implementation. So why not use that for Mojo? Well, let's take a look at it. We'll assess it here and see if it works for us. So there's actually 3 different lowerings in LLVM. There's a switched resume lowering, which has 1 resume and 1 ramp function and a destroy function, and also apparently a cleanup function. I'm not really sure what that one does, but and there's a context for each resume, or there's only 1 resume, so frame is stored in the context. The return continuation is similar, except it returns the function pointer to the next resume function. So there's a resume function for every suspension point. The front end also has to specify the size of the fixed buffer that you send to each resume point. We don't really want to define the front end to define that. We also don't want a resume function for each suspension point. This is a much less commonly used lowering, so it's not really tested, tested by usage, so we didn't look into that one. The async lowering is used by Swift. That is similar to return continuation in that it has multiple resume functions, 1 for each suspension point, but it is also closer to switched resume in that the frame is stored in a context that's past each resume function. So let's start with switched resume. Is that going to work for us? This is what C++ uses. So back to our little toy example, I've changed it so it's using C++'s API here. So now we no longer have our custom coroutine where we have this task, which actually is also user-defined, but it's wrapped around a coroutine handle that the compiler generates. So at least we don't have to explicitly specify all the intermediate state, so we've saved some work. And we're not calling that same function that we turned into a state machine. We have a resume function now, so a little bit better. The main differences come in the kernel code, so now we don't have to have our state machine. We can use keywords like co-await, co-yield, which are, co-yield is like suspend, but I'm not done yet, just write to the return, but keep going. Co-return will mark it as done, and co-await spawns a child coroutine. So it's a little cleaner, looks nice, but what we really care about is what's going on underneath the hood, because obviously we're not C++, we're not gonna share the front end. So what does the frame look like? What's getting generated? So to analyze that, I've simplified our example. So it's not really illustrating the utility anymore, but at least we can look at things a little bit more simply. So we've got one suspension point, and we only have one value that crosses that. This is the task that I mentioned earlier, so that's where that coroutine handle is a handle to the compiler-generated frame. So what does that frame look like? I looked at the IR that's generated from this code, and then there's our frame, so let's step through it a little bit. So we got a pointer to the resume function, pointer to the destroy function, that's fine. We've got the promise type, which is I32 in this case. And then we've got these other values, which are the most interesting. The two first 32-bit integers are the frame, and the last is the state. But why is it storing two 32-bit integers if there's only one value used across suspension points? So let's look at the ramp and resume to see why. Actually, our operation was cloned, which is sometimes okay. I mean, sometimes an operation is cheaper than the load store into the frame. But in this case, we are doing this twice, and we also have two loads and two stores. So it doesn't really make sense. But it does mean that it's only storing the values it needs for the resume because the input is used in that second one. So this doesn't really tell us much, but let's not run the optimizations. Maybe something is interfering with it. So I ran an O0, and now we're just storing everything. So we have the inputs, we have the intermediate value, we have the final value, which is the only one that we care about. So that didn't really help. We also have a value for each suspension point that indicates whether or not to suspend. This might be specific to C++, but in any case, we don't really want to store this extra information in the frame. We'll use other mechanisms to eliminate a suspension point if it's necessary. So what about the frame? Where are we allocating that? I mean, nothing escapes here, so maybe we can just put it on the stack. But actually, we're putting it on the heap anyway, so that's not great. Let's give a little scorecard here. So the memory footprint, all values were stored on the frame, so we don't really want bloated frame sizes and unnecessary store ops. How is the coroutine allocated? Well, it appears that the heap allocation was not elided when it should have been. The IR footprint, not too bad. We have one ramp, one resume, but we don't need a destroy or a cleanup function. In Mojo, we have ASAP destruction, so we can get along with just a ramp and a resume. And were they hot started or cold started? We'll get into definitions of those later, but we did see that the first state of the resume function was moved into the ramp, so I'll give it a partial score of it was okay. But all in all, maybe not what we're looking for. But not all hope is lost because we have this other lore we can look into, and it's used by Swift, which is pretty popular, so it probably works pretty well. So let's translate our example to Swift here. And I was a bit surprised to see so many integers stored in such a simple function here. So I added just like another intermediate value that shouldn't be stored in the frame, but it was. So this is not great for frame size. Let's look at the IR footprint. So how many functions are we generating? We have one for every resume or every suspension point. So we have the ramp, and then in this case, two resume functions, which is not ideal because having too many functions in the IR can slow down some of the other passes that run on a function grain. So, and it's also difficult to reason about. So we'd rather not do that. As a historical note, we did try and do that, but we observe inactive values being stored in the frame. We observe allocations not getting optimized away. We also had issues parallelizing LLVM because the co-row pass depended on multiple functions living in the same module. So we decided to step away from it, and our goals moving away from it were we wanted finer grained control over the size of the frame. We wanted to control the number of functions generated, and we wanted to control the order of the lowerings so we could optimize allocations. All right, so we're back to the drawing board. How do we design an async lowering that achieves these goals? And this brings us to part 3, which is the MLIR coroutine implementation. So the first thing we're going to do is we're going to define a dialect. We're not going to lower these functions until pretty late in the pipeline, so we want a succinct way to represent them beforehand. The next thing is we know we eventually have to lower them, so when do we lower them? And to do that, we need to identify the optimizations we want to support and if they depend on other passes and when those passes are happening. Once we identify where they happen, then we can define the actual transformation because we've identified the input. So here's the dialect that we designed. I've divided it into two categories. So kind of have two things that we're generating. We have the functions, then we have the frame. I'm going to focus on the abstractions of the function and kind of not go into the teal operations. The teal operations are for accessing elements that are stored in that generated frame, and they're really important for writing like runtime libraries or supporting error handling, but that's outside the scope of this talk. So I'm going to focus on code.invoke, which is a call to the yet to be generated ramp function, code.suspend, which represents a suspension point in a function, code.await, which is an implicit suspension point that also represents setting some fields in the spawned child coroutine. So if I have a code.await, I want to set the callback to the parent coroutine. So instead of writing all that out every time, we have a succinct way to represent it. And then code.destroy, which is generally not embedded in the language, that's going to be emitted by other passes that are responsible for handling lifetimes. OK, next, talk about the order of the lowering. So what optimizations do we want to support? Well, we want to support both hot and cold coroutines. Again, we'll get to what that means in a moment. We want to promote heap allocated coroutines to the stack. And it's also important to consider what the IR looks like when we lower this, because we don't want to have to add anything to the IR in order to make it behave correctly. So specifically, control flow should be unstructured when we lower the resume function to a state machine. OK, so I keep talking about these hot and cold started coroutines. What does that mean? Well, generally, a coroutine is lowered into a ramp and a resume function. You can put the first state of the resume function into the ramp function. That makes it a hot started coroutine. And so what that means is that when you invoke a coroutine, you are not only creating it, you are executing it. In contrast, a cold started coroutine, the ramp only allocates the memory and configures the coroutine and then returns it. It doesn't start it at all. We really want a hot start whenever we can because it means smaller frame sizes and one less function call to complete the coroutine. But we can't always do that. On the right, it's on the right. That's not eligible to be hot started because we create it, but then we want to, let's say, like spawn a thread and tell the thread to go run it. So we don't want to start it yet. So how do we generate hot versus cold coroutines? Well, they have different ramp functions, so we need to know ahead of time which ones are going to need which ramp function. So we're going to introduce a new representation for that. I'm calling it hot invoke here. And we want to transform the pattern on the left into the pattern on the right. So if we are immediately calling the resume function of a coroutine we just created, that's a hot invoke. So we can easily implement that with a canonicalization pattern. OK, so as we identify these transformations, let's start keeping track of them so we have our lowering plan. I didn't really go into how the parser emits await and invoke. It's kind of outside the scope, but we'll just assume that we have that. The next thing was the transformation we just mentioned, the canonicalization. So now let's talk about when we lower away the rest of the code dialect ops. So we mentioned that we want to align heap allocated coroutines. How do we plan to do that? Well, we can only align the allocation if it doesn't escape, and it always escapes the ramp function. So we have to inline the ramp function first. So we know that we have to lower them before inlining. And then we will use a heap to stack promotion pass to promote those allocations to the stack. But we're not done yet. So remember that how I mentioned control flow can be a little tricky in some forms. So at the stage where we have the lowering of the async function, the control flow looks something like in the green box there, where it's nested. This means that like control flow is defined relative to operations and not like function scoped, which makes it really hard to express that we want to like continue execution inside an op that we have no way of referencing at the function scope. Or we can just wait till control flow is lowered, where we can then just easily say, hey, year state 1, jump to block 7. So that the reason we don't push everything to the end is because we rely on structured control flow for the memory promotion. So now it's the easiest way to do both is to just split it into 2 steps. So we will lower the functions, we'll inline, we'll perform heap to stack, we'll lower control flow, and then we'll transform the resume function into a state machine. Okay, so we've defined the ordering of the ops. Now let's focusing on that how. How do we perform this transformation? The state machine transformation is pretty simple, and I already showed the example of the canonicalization. So let's focus in on the lower async functions pass. Here's a general outline of what's going on. I'll break it down into like 4 steps. We pre-process, we perform the frame calculation, we generate the ramp and resume, and then we lower all those frame ops to get element pointer ops into the frame that we just generated. So we'll start with lowering implicit suspension points. So here's the reason we have co-await, because this is what co-await actually represents. So there's kind of a lot going on here, but we essentially set the call back to the parent and extract the results from the coroutine and then destroy the coroutine. The next step is calculating the frame. This is kind of a tricky step. One of the things that's tricky with this is that control flow that I mentioned is structured at this stage. So we kind of have to pretend that it's unstructured by creating virtual blocks represented by by operations. So kind of like drawing boundaries around our code here. And then what this algorithm attempts to compute is what values to store in the frame. So if there's a path from the definition to a usage that passes a suspension point, it needs to live on the frame. It can be kind of tricky because you can't just take all unique paths. So for example, in this path, if you just took the unique paths and stopped at cycles, you wouldn't notice that X needs to live on the frame. So some interesting challenges. Another interesting challenge is that sometimes cheap operations are it's better to clone them than to put them on the frame. So for example, if I have a pointer arithmetic, we shouldn't store another value that we're already storing in the frame. We should probably just clone that offset. Finally, stack allocations, they have to be replaced with frame allocations, and we can't rely on SSA USDEF chains because they can't be modeled that way. So we use these lifetime markers to identify if stack allocations need to be stored on the frame. Another challenge is that we might have a coroutine that needs both a hot and a cold ramp, but ideally we'd only have one resume function because again, we want to reduce our IR footprint. So to do this, we just store any state that's specific from the initial state to the first state at the tail of the frame, and that way we can just cast it to the larger size in the first state, which is only reachable from a cold started coroutine. Finally, we can generate the functions now that we have our frame. And this is just an example of what that might look like. So we have a cold started coroutine here, and it turns into a ramp and resume, and we can see that the suspension points are still intact. So I went over some material in this talk, but there's still a lot more remaining that's outside the scope. I didn't cover lifetimes of values in the frame. I mentioned that Mojo has ASAP destruction. Thank you. There's how do we do error handling, storing those values in the frame, debugging, callbacks must be marked as must tail, and if there's no suspension points, we shouldn't pay the price of asynchronous call. Another interesting question is just from a front-end standpoint, like why do we have to mark functions with async? So that's all I have for today. Thank you.
Thank you, Steffi. We can take a couple of questions. We a bit over time, but yeah, go ahead.
So the entire pipeline is done before LLVM passes?
I'm sorry?
The entire lowering of the coroutine MLIR dialect has happened before the LLVM passes?
Yes, correct.
Okay. I have a separate question. When you say stack promotion, is it always the stack though? Could it be the color coroutines frame when you do the stack promotion?
That is to move the whole coroutine frame.
No, I mean, if you have a coroutine calling another coroutine and the callee coroutine happens to be inlineable, I mean, the ramp function happens to be inlineable, does it become promotion to the caller coroutines frame?
We should inline all the ramp functions ahead of time. So if there's a child one, that would be inlined also. Maybe I don't understand your question.
Okay, maybe you can take this offline.
Okay, sorry.
Do you know why the LLVM async coroutines store those extra values? And could you have adapted that approach to be used in Mojo as well?
I didn't debug why there were extra values in the frame.
Okay.
Sorry.
Thank you.
Thank you.
Out of curiosity, how do you approach making the coroutines debuggable from the end user perspective?
We have not addressed that yet.
All right, fair enough.
Do you know how the coroutine implementation compares to Rust? Since Rust also uses LLVM, but as far as I'm aware, they don't use the same mechanism as C++ as well, and they happen to not even do any heap allocation in the first place that they need to be lighted. How does this differ from your approach, and what are like the trade-offs?
I'm not familiar with Rust implementation. I did notice that they didn't use or at least I don't think they use the same backend as LLVM. So I'm just not familiar enough with it to compare.
Okay, thank you.
Mm-hmm.
Hi, thanks for the talk. So do you have any statistics in terms of your implementation versus C++ one? And I assume in LLVM, I mean, like in terms of how many heap allocation have you removed, or?
No, the feature is brand new, so it hasn't really been battle tested yet.
So maybe next year it'll.
Maybe next year.
Thank you.
Yeah.
We have time for a couple more questions. Last call. If not, let's thank the speaker once again.